Hello friends, after completing the synthesis of naphthalene, now we will see the reactions of naphthalene. So let us go to the presentation. Just hold on till I make it full screen. Okay, so now we are going to study the reactions of naphthalene. The reactions are oxidation, reduction, and electrophilic aromatic substitution. So first, let us see the oxidation reaction. Naphthalene reacts differently with different oxidizing agents. When naphthalene is treated with chromium trioxide and acetic acid at 25 degrees Celsius, it gets converted to 1,4-naphthaquinone. When naphthalene is treated with oxygen in presence of vanadium pentoxide at about 400 degrees Celsius, it gets converted to phthalic anhydride. Then, when naphthalene is treated with ozone, the two double bonds here at naphthalene react with ozone, and finally the ozonoid breaks down to form phthalaldehyde. The ozonoid breakdown happens in presence of zinc. Now, remember, this is a very frequently asked question in the examination. Complete the following reactions. Either they will give naphthalene and the reagents and will tell you to write the structure of the product, or they will give naphthalene, the structure of the product, and will tell you to write the reagents, or a short note of 3 marks on oxidation reactions of naphthalene. Okay, in such cases, it is absolutely necessary that you know all these structures. So how to remember this ozonolysis occurs at only these two double bonds. Okay, the benzene ring, the other benzene ring is intact. So the ozonolysis occurs over here, and so the breakdown will be here and here, and therefore phthalaldehyde will be formed. In case of chromium trioxide, the temperature is less, and so the ring structure of the second ring is intact. There is only a oxidation at these two carbons and the double bond. Whereas in presence of vanadium pentoxide, the ring structure is not intact, but it is not completely broken also. Okay, so just remember 1,4-naphthaquinone in presence of chromium trioxide, phthalic anhydride in presence of oxygen and vanadium pentoxide, and ozonolysis followed by treatment with zinc dust in presence of water gives you phthalaldehyde. Going to now reduction reactions. Again, it is the same. There are 3 reducing reagents which give different products. When naphthalene is treated with sodium and ethyl alcohol, one double bond is reduced and it gives 1,4-dinitronaphthalene. Okay. When naphthalene is treated with sodium and isoamyl alcohol, both the double bonds are reduced and it gives 1,2,3,4 tetrahydronaphthalene. When naphthalene is treated with hydrogen and either platinum or nickel, this is a very strong reducing agent, very strong hydrogenating agent, and therefore decalene is formed. Now, one simple way to remember, it is not logical, but it is a simple way to remember between these two. This alcohol is a small alcohol and therefore only one double bond is reduced. This is a larger alcohol and so both the double bonds of the ring are reduced. This is not logical, but it works. Okay. Going to the next reaction, that is electrophilic aromatic substitution. before we go to electrophilic aromatic substitution of naphthalene, we will discuss in short about electrophilic aromatic substitution of benzene. Okay, when there are 6 positions on benzene, but all these 6 positions are equivalent, and therefore electrophilic aromatic substitution, the mono substitution gives only one single product, irrespective of whether Y is here or here, etc. Okay, because all the positions in benzene are equivalent. That is not so in naphthalene. In the previous lecture, we saw there are 2 distinct positions in naphthalene. These 2 positions can give rise to products, 1 substituted naphthalene or 2 substituted naphthalene. Now let us see which is the preferred product. This is an electrophile, and when this electrophile is attacked by the benzene ring, let me write this down. This is attacked by benzene ring. What happens is the substitution can take place either at position 1 as is shown over here, or we will discuss the position 2 later. So when the substitution takes place at addition takes place here at position 1, carbon number 2 gets a positive charge, right? This carbon number 2 getting a positive charge, this positive charge can come to carbon number 4 by resonance like this. Okay. And this ring resonance, the other ring resonance, contributes to 2 more structures. So what happens? The attack on C1 generates 4 resonating structures. Everybody understands this? Attack on C1 generates 4 resonating structures. Now let us see what happens on attack at C2. This is naphthalene. I am writing Y plus over here. Okay, this is Y plus. This is an electrophile. And when naphthalene attacks the electrophile like this, if the substitution takes place at position 2, charge comes, positive charge comes on carbon number 1. Now, within this ring, the charge cannot rotate because this double bond is away. Is everybody getting this? This double bond is away. So, the other resonating structure for attack on C2 is the ring resonance of the other ring. Just have a look at this. Because of the ring resonance of the other ring, just see this ring versus this ring. This is a ring resonance of the other ring. The charge does not rotate on the ring. And so, attack on C2 produces only 2 resonating structures. Now somebody will ask me, if this is the resonating structure, one of the resonating structures, then why can't we write like this? Okay. That way, you will say the charge will move from one position to other, or in other words, the charge will be delocalized. But can this happen? No, this cannot happen. Why? That is because if such movement takes place, both the rings are losing their aromaticity. Do you realize? And therefore, such type of resonance is not considered. So now, we are left with the facts that attack on C1 generates 4 resonating forms, whereas attack on C2 generates 2 resonating forms. In other words, the intermediate is more stabilized if attack occurs on C1. And therefore, the electrophilic aromatic substitution on benzene occurs on naphthalene, I'm very sorry, electrophilic aromatic substitution on naphthalene occurs at C1 preferentially. Okay. Now, this is also a commonly asked question, why electrophilic aromatic substitution occurs on C1 preferentially. And you will have to write these resonating forms. You will have to write the two resonating forms of attack on C2. Then say that the intermediate formed when the attack happens on C1 is stabilized to greater extent by resonance than intermediate formed by 2. Therefore, electrophilic aromatic substitution on naphthalene occurs at C1. Let us see examples of electrophilic aromatic substitution. First one, this is naphthalene. When it is treated with a nitrating mixture, that is HNO3 and H2SO4 at 60 degrees, the product that is formed is 1-nitronaphthalene. This is a preferential product. Okay. Now, second reaction. Let us see halogenation of naphthalene. When naphthalene is halogenated, I have written here the reaction bromine CCl4 and reflux. Since the boiling point of CCl4 is much lesser, the refluxing temperature will also be lesser. Okay, so naphthalene reacts with bromine in presence of CCl4 to give 1-bromonaphthalene. Characteristic of this reaction as compared to bromination of benzene is that Lewis acid is not needed. So why is that so? Why is Lewis acid not needed? To answer this question, we have to understand that when electrophilic aromatic substitution occurs in benzene, I will draw the structure over here, benzene electrophilic aromatic substitution. Okay. So here is H, here is Br, there will be a positive charge over here. Okay. This is so. When electrophilic aromatic substitution occurs in benzene, the intermediate has lost its aromaticity. Okay, the aromatic stabilization to some extent, because there enters a sp3 hybrid carbon. Okay, the ring loses its aromaticity. But what happens in naphthalene? Only one ring loses its aromaticity. The other ring is still aromatic and therefore more stable. And so, the electrophilic aromatic substitution in naphthalene is easier than electrophilic aromatic substitution in benzene. Why? Because even though substitution occurs, only one ring loses its aromaticity. So naphthalene reacts faster, and so the need for Lewis acid is eliminated. There is no AlCl3, there is no BF3, if you can see over here. Okay, now next we go to sulfonation, then to Friedel-Crafts acylation. The sulfonation, when naphthalene is treated with concentrated sulfuric acid, sulfonation occurs. At 80, if the reaction is carried out at 80 degrees, the product formed is naphthalene 1-sulfonic acid. Whereas, if the reaction is carried out at 160 degrees, the major product formed is naphthalene 2-sulfonic acid. Now, why it happens? This can be explained on the basis of kinetic versus thermodynamic control of the reaction. Look at this product. This is a product expected because when there is one substitution, there are more number of resonating structures. When there are more number of resonating structures, the energy of the intermediate is lowered down, and so the reaction can happen at 80 degrees, where naphthalene 1-sulfonic acid is a major product. Now, what happens when you raise the temperature to 160? See, when you raise the temperature to 160, there is sufficient energy available for naphthalene 2-sulfonic acid to be formed. And naphthalene 2-sulfonic acid is finally the thermodynamically stable product. At 80 degrees, why naphthalene 2-sulfonic acid doesn't form? That is because there is not sufficient energy available to form naphthalene 2-sulfonic acid. But at 160 degrees, that can happen. So, this product, naphthalene 1-sulfonic acid, is called as kinetic product, whereas naphthalene 2-sulfonic acid is called as a thermodynamic product. Now, if you plot a graph, energy profile diagram, what it will look like, the starting material is same. This is 1-sulfonic acid, okay? The energy of the transition state and the intermediate, actually it should be a two-step process, okay? But I'm simplifying this. Now, for naphthalene 2-sulfonic acid, how it looks like? Understand this, only if you can provide this energy, naphthalene 2-sulfonic acid will be formed. Next reaction is Friedel-Crafts acylation. Here again, two different solvents give two different products. When naphthalene is treated with acetyl chloride in presence of AlCl3, if you use ethylene dichloride as a solvent, the substitution occurs at position 1. Okay, a ketone is attached, acyl group is attached to position 1. Whereas if you use nitrobenzene as a solvent, then you will see that you get a 2-substituted naphthalene. Again, the reason is same. This is kinetically controlled. This is thermodynamically controlled. But when you use a non-polar, this is a more non-polar solvent, whereas this becomes a more polar solvent. If you use a more non-polar solvent, the product precipitates and therefore there is no chance of reversal, whereas in a polar solvent, the product does not precipitate. So even if one substituted product is formed, it can revert to a 2-substituted product. Remember, in case of exam, up till now, I have never seen anybody asking the reason, but this is the product, 1-substituted product when EDC is used and 2-substituted product when nitrobenzene is used. Now, coming to second substitution on naphthalene. When there is already an existing group, how does electrophilic aromatic substitution go? It is easier to remember this, okay? If the existing group that is already present on the naphthalene ring, if it is orthopara directing, then the second substitution occurs on the same ring. Okay, so here is it, 1-methoxynaphthalene. When it undergoes nitration, then there are two products obtained. 4-nitro product is the major product, the substitution occurring at 4 position, and 2-nitro product is a minor product where substitution occurs at 2 position. Okay. As against that, when the methoxy group is present at 2 position, so in 2-methoxynaphthalene, when you carry out nitration, the product obtained is 1-nitro-2-methoxynaphthalene. Okay. Remember that when there is a electron donating or orthopara directing substituent, already present on the naphthalene ring, the second or the incoming group also goes on the same ring, either at position 4 or at position 2. Here, there is 4 position not available, so it goes on position 1. Okay. Now, let us see what happens when Y is electron withdrawing. The already present group is electron withdrawing. So, if Y is electron withdrawing, then what happens? The second group which is entering in goes on the other ring. So, it goes either at 5 position or at 8 position. This is the case even when the first group that is already present on naphthalene ring is present at 2 position also. Still, 5 substituted and 8 substituted products are formed. Okay. This will also give 5 substituted and 8 substituted products. Now, questions I will give after phenanthrene and anthracene. Okay. So that is all about today's lecture on reactions of naphthalene. Our next lecture will be synthesis and reactions of phenanthrene and anthracene. So, thank you so much. If you like the lecture, please hit the like button and subscribe to the channel. Thank you.